So you will quickly find out in studying optimization, optimization is just about linear algebra and calculus. If you know everything about linear algebra and calculus, and you are already very fluent in them, which I'm not, right? So that's why I need to study optimization. If you are very fluent in using them, you don't need to study optimization. You can rederive everything I teach in this class. So that's why we are teaching this lecture now. Okay, so first of all, disclaimer. It is not possible to teach everything within one lecture. All the theorems are given without proofs. Maybe we can talk a little bit about the proof intuition for each one of those theorems. But I would highly recommend this YouTube channel called 3 Blue, 1 Brown, listed in the reference later on. The reason I recommend this channel is it gives you not only the results, but some geometric intuition. So one of the things is that typically you'll find in most of the engineering mathematics class, the professors would focus on calculation, right? How do you calculate a matrix inverse and so forth. But nowadays you can almost compute everything using computers. You don't really need to exactly remember how to calculate a determinant or inverse. The thing that is more important is the intuition, right? When you try to derive something new, how do you use the intuition to come up with a new theorem, right? So the way of doing mathematical research and solving mathematical problems are very different. So if you solve some homework problem, let's say in optimization, you already know that that statement is true. That's why you are proving that, right? Otherwise, there is no solution. And then when you are doing research, the hardest thing to do is coming up with conjecture, right? What statement are you going to show that is true, right? So that will require some sort of intuition. Okay, so I would highly recommend you to take a look at this YouTube channel. Okay, so let's start with linear algebra. Start with things that are very simple. So how do we have anyone who doesn't know what a matrix is? Just quick show of hands, because we have some, even in our undergrad curriculum, we did teach linear algebra, right? Okay, yeah, that's good. Yeah, so just quick review. I assume everyone is familiar with those notation. So a matrix is written as, so here we only talk about real numbers, right? We don't talk about complex numbers in this class. So A is a matrix with dimension m times n. And then you can denote a vector by x with dimension n, right? Okay, so the x is called a column vector if it has n rows and 1 column. And it's called a row vector if it has one row and n columns. And typically we write them as x transpose. And by default, if you are given a vector, just assume it's a column vector, right? That's what people typically assume. So here's a column vector with n dimension, right? So you write each of the element as x sub I. Yeah, and then without loss of generality, you can write a matrix this way with m rows and n columns. And then you can denote each row as a sub I. So you have n different rows in this matrix here. And then each of these is a column vector here. And then you can denote the ith row of a matrix by transpose. Typically, if you write a row vector, you use A transpose instead of A, right? So by default, a column vector is A row vector is A transpose. So now it has m different rows, right? So now the A and the A1 and the A1 here are different, right? Because one representing all the columns of A, the other represent all the rows of A. Okay, this is just a notation. And then another simple thing in linear algebra is matrix multiplication. Just quickly review the notation here. Okay, so if you have matrix A, which has m rows and columns, and B with n rows and p columns. Remember, in order for matrix multiplication to happen, you need to have, the number of columns in A must equals to the number of rows in B, right? In order for matrix multiplication to happen, and then you can write A as like a row form and the B in a column form, and then the ij element of C is at the ith row of A inner product with the jth columns of B, right? This is just how matrix multiplication occur. Okay, I'm sure in most of the engineering mathematics class, you are very comfortable with doing those calculations. Okay, then let's give some examples of matrix multiplications. Perhaps the simplest example of matrix multiplication is one vector multiply another vector. Right? So if you calculate x transpose y, this is called the inner product of two vectors, right? So maybe a quick question to the audience is, what is the geometric meaning of inner product? Of course, you can multiply these two vectors very easily, right? Since they have the same dimension, you just add them up. So here I should write it down as, here's a typo here, xi, yi. This should be y. Okay, yeah. So if I give you, let's say, two vectors, this is x, and this is the origin, this is y. What does it mean to multiply these two vectors? Yes?
Taking the dot product projects x onto y.
Yeah, exactly. So you project x onto y, and then basically you multiply this the length of the projection with the length of the y. So that is the dot product, right? And then the other thing is called the outer product of two vectors. So you can take two vectors with any arbitrary dimension. Let's say x has m dimension, y has n dimension. But then instead of using x transpose y, you do x y transpose. So you have a column vector multiply a row vector, right? In this case, it will give you a m times n dimensional matrix. So this is called the outer product. Okay. And then a slightly more complicated operation is a matrix vector multiplication. This is perhaps you have seen a lot in many different applications where you can write y as a times x. So let's assume a has dimension m times n, and then x is an n-dimensional vector, right? So again, if you want to do the calculation, you can write a1 all the way to am in row form, and then each of the entry would be ai transpose x, right? So this is nothing but a simple matrix multiplication. So if you look at a times x in this form, it doesn't give you any intuition. So, but I think I would prefer to look at matrix multiplication in a slightly different form, where you can treat ax as a linear combination of all the columns of A. Okay, so here the coefficients are x1 all the way to xn, right? So you are taking a linear combination of those columns in the matrix A. So a way to view this, if let's say A is an n by n matrix, x is a n-dimensional vector, right? So you can view this as what is called a linear transformation, right? So originally you have a vector whose coordinates are x1 all the way to xn. And now you are transforming this vector to a different coordinate system using the matrix A, where each of the columns of A is denoted by a1 all the way to an, right? So then you are going to transform the first dimension to this vector a1 and so forth. Okay. Yeah, and then what are the properties of matrix multiplication? You can easily verify it, right? First of all, matrix multiplication is associative. You could first calculate A times B, or you could first calculate B times C, and then use that to multiply A. And it's also distributive. It's very straightforward to show that. But matrix multiplication in general is not commutative, right? This is also very easy to see because in order for matrix multiplication to occur, then the number of columns of A has to be equal to the number of rows of B. But then BA may not even exist, right? So because the number of columns of B may not equal to the number of rows of A, right? So this is in general not equal to each other. Okay, so then another notation is transform, matrix transform and symmetric matrices, right? So if you, not transpose, so transpose, right? So the transpose of a matrix A is written in this notation A transpose, right? So if A is, you basically flip the column and rows of matrix A. Where the ij's element of A transpose is equal to the ji's element of matrix A, right? And then there are some very simple properties. If you take transpose twice, it's the original matrix. And then if you want to do A times B, then transpose, then you have to do B transpose, A transpose. It is very straightforward to verify that algebraically. Okay. And similarly, if you have A plus B transpose, it's you take the transpose respectively and add them up, right? Those should be very easy to verify. And if A is a square matrix, n by n matrix, then a matrix is called symmetric if A equals to A transpose. Okay. So most of the matrices we deal with in class will be symmetric matrices. The reason is when we consider n by n matrices, most of the applications are related to we are interested in calculating some quadratic functions x transpose, let's say ax. A is let's say A is an n by n matrix, and usually you assume A is symmetric in this context. The reason is even if A is not symmetric, since we are interested only in x transpose ax, we can always redistribute the weight to make it symmetric, right? Because if you have x1 times x2, it's the same thing as x2 times x1, right? So that's why we assume it, in general, A is symmetric here. And a matrix is anti-symmetric if A equals to minus A transpose. That's just a definition. And then you can very easily verify that any square matrix can be decomposed as a symmetric matrix and anti-symmetric matrix, right? This part is clearly a symmetric matrix, and then you can take the transpose of this part and quickly show it is an anti-symmetric matrix. Okay. So far, so good. Right. Okay. Yeah. Yeah, and then the other concept is called the trace of the matrix, right? So the trace only apply to a square matrix. The definition is you add up all the diagonal element of the square matrix. Okay, so it's a summation of I from 1 to n, A sub ii. Okay, and there are some easily proved property of trace. Most of these properties can be verified easily just by definition of the trace. Of course, the trace of A is equal to the trace of A transpose. And if you add up the trace is like a linear operator. You could separate A and B. And then if you have a scalar R, a scalar T times A, you can take the scalar out, right? Because you are essentially summing over the diagonal elements. So what's more interesting here is the trace applied to matrix multiplication. Okay. So if you have square matrices, right? So multiplication can always occur, right? Even though I said A times B does not necessarily equal to B times A, their trace will be the same. So you could try to verify those results. And similarly, if A, B, C are three matrices, you could sort of rotate their sequence right? You could maybe apply this property to this problem here, and then you will get, you could change the sequence of their multiplication if you are calculating their trace. Okay, and then you will see some applications of trace in optimization, especially when we talk about semi-definite programming. Okay, so another concept I find not every student knew that from last time I taught this class is called the norms of vectors and matrices, right? So just a quick review. If you have a vector, what does the norm mean? So intuitively, you can think about the norm as a way of measuring the length of the vector, right? So here, probably the most commonly seen norm is called the Euclidean norm or the 2 norm, right? So if you have a vector x, it is basically taking the square of each entries of this vector x and then taking the square root, right? So the Euclidean norm calculate the Euclidean distance of this vector from the origin, right? How long is this from the origin in Euclidean space, right? If you want to calculate the distance between 2 points in Euclidean space, you just take the difference of these 2 vectors and take the Euclidean norm, right? And one norm is the summation of the absolute values of each entry, okay? And infinity norm is taking the maximum of the absolute value of each entry, okay? And all those norms can be generalized using this p-norm formula, okay? So here, you have the p-norm equals to, you take each entry of this vector raised to the power of p, and then take the summation raised to the power of 1 over p, where p has to be greater than or equal to 1. Okay. So here you can quickly verify, let's say if p equals to 2, you clearly reproduce the Euclidean norm, right? When p equals to 1, you reproduce the 1 norm, right? And if you take the p to infinity, right, as this order of polynomial grow, the largest term will dominate the rest of the term, right? So that's why it is the maximum of the these absolute value here, okay? So now this is vector norm, and those are the most commonly used vector norm, and it should be quite intuitive. If you forget about it, just think about the distance between 2 points, and then you got the Euclidean norm, right? And the 1 norm is also called, some people call it the Manhattan distance. Right. So when you are traveling in Manhattan, you can only travel using those vertical streets, right? You cannot just take the line segment of 2 points. You have to use, either vertical or horizontal, right? So that's the absolute value. Okay. Yeah. And then, what exactly is the definition of norm, right? So how do you sort of extrapolate the definition of vector norm to matrix norm? This is the real definition of what is a norm function, right? So before we go to matrix norm, let's take a look at these definitions. So it says for any function from Rn to R, if it satisfies these 4 properties, then it is the norm function. So first, any norm should be non-negative, right? Since you can think about intuition is that a norm defines a distance, it is non-negative. And then the second property is definiteness, meaning that fx is 0 if and only if this vector itself is a 0 vector, right? So any non-zero vector, this should give out a non-zero value, right? Because it is measuring the length of the vector, right? Any non-zero vector has a length of non-zero, right? So this should be also intuitive. And then it also has a homogeneity property. If you multiply a scalar to this vector, then you can take the scalar out, but then you have to use the absolute value, right? Because the norm is describing the length. If t is a negative number, you cannot just multiply the negative thing out, right? And the other thing is triangle inequality, right? So fx of y less than equal to fx plus fy, right? So in Euclidean space, this is very intuitive to show, right? If you travel directly from point A to point B, then the length should be less than you travel first to point A, then to point B, right? Yeah. So that's sort of the intuition. And then you may wondering, why do we need those? This four property looks like very abstract, right? If you want to remember norms, perhaps the previous slide is easier to remember. So that's the thing with studying mathematics, right? Usually the mathematicians will give you some abstract definitions, and then they will use those sort of definitions to prove some properties regarding norms, right? So if you have these four property holds, maybe you can prove some other properties, right? But then as long as the norm function you propose satisfy these four properties, it will satisfy the properties they have already proved, and then you don't need to redo the math again. Okay, that's why they want to define in a such an abstract way, rather than just give you some examples of norms, right? Okay, so if you want to define norms in the matrix form, these are the two most commonly used matrix norms. The Frobenius norm is quite intuitive. You just take each entry of this matrix and then square them and sum them up, and then you take the square root. So you might get confused because the Frobenius norm is similar to two norm in vector norm, right? So why do people define matrix norm differently, right? So here the two norm of a matrix is not the Frobenius norm. It's taking the largest eigenvalue of A transpose A, right? The reason they define this way is that they want to make the matrix norm compatible with a vector norm, right? The way they define that, it can be compatible with a vector norm. But then perhaps if you don't want to go to the details, just sort of remember there are two most commonly used matrix norms here. Okay. Yeah. So there are one concept I want to explain here is linear independence and linear dependence, right? If I give you m vectors x1 n vectors with m dimension x1 all the way to xn. So I call those vectors linearly independent if no vectors can be represented as a linear combination of the other vectors, right? So if you can pick one vector, let's say without loss of generality, let's say xn can be represented as linear combinations of the rest of the n-1 vectors, then they are linearly dependent, okay? And then here's an example, x1, x2, and x3, and then clearly you can show that x3 is dependent on x1 and x2, okay? Yeah. So here's another definition. Again, this is just a cheat sheet. I will go over the cheat sheet without any proof, okay? So what is the rank of a matrix? First of all, you can define column rank and row rank, right? So a column rank means the size of the largest subset of linearly independent columns, right? In other words, that is the largest number of linearly independent columns you can find from this matrix, and the row rank is the largest number of linearly independent rows you can find from the matrix. And this is a sort of, maybe it's called fundamental theorem or something in linear algebra, is the column rank equals to the row rank. It's referred to as the rank of A. Okay, so did you prove this property in the class in previous semester for the first year students? No? Does anyone know roughly how to prove this theorem? Like why the row rank and the column rank of a matrix are equal? Okay, so maybe you talk about this like row echelon form. How do you do those operations to bring the matrix into O row echelon form? And then you can show that when you bring that to that form, the row and column ranks are equal. Okay, and then these what is that called? Elementary operations or something does not change the rank of the matrix. That's like roughly how you show that. And then since you know the column rank and row rank are equal, some of the properties hold, right? Then, of course, the rank should be less than equal to m and n, right? So because m and n are the largest number of columns and rows you have, since the rank is equal to the column rank and also equal to the row rank, it cannot be bigger than the number of columns or the number of rows. And then if the rank of A equals to the minimum over m and n, then we say A is a full rank matrix. Okay, right? That's the largest rank you can get. And this property should be pretty trivial because you just take the transpose and then the row rank becomes column rank and vice versa. So here's another property. The rank of A times B should be less than the minimum rank of A and the rank of B. Why this is true? You don't need to write a rigorous proof, but intuitively why this is true. Any thoughts?
So
Yeah.
when you multiply two matrices,
Yeah.
Either the number of columns or the number of rows would be the minimum of one of the matrices.
Yeah.
So if the rank, since we have defined rank to be the minimum
Yeah.
of a particular matrix, either column rank or row rank,
Mm-hmm.
then we need to, like, this has to be satisfied that it has to be a minimum of
Right.
the individual.
Yeah. So you can, roughly that's the intuition. So you can kind of view the columns of A times B as a linear combination of all the columns in A, right? So since they are linear combinations of the columns of A, they cannot get bigger than the rank of A. And similarly, you can view A times B as, so all the rows as linear combinations of rows of B, right? So it cannot get bigger than the number of linearly independent rows in B, right? So that's why this is true. And here, this is another property. The rank of A plus B less than or equal to the rank of A plus rank of B, right? So roughly why this is true. Let's see. Yeah, so this is relatively simple, right? So if you consider all the linear combinations of, let's say, the columns of A plus B, right? They of course, they can be expressed as linear combinations of columns of A and linear combinations of columns of B, right? So that should be straightforward. If you can express them as a linear combination separately and add them up, then they should be less than the rank of A plus the rank of B. Okay. And then there are concepts called the inverse of the matrix, right? So the inverse of a square matrix is denoted as A inverse, right? And then an inverse is unique. The other important property to remember is that the left inverse and the right inverse of a matrix are the same matrix, right? So here, if you consider you want to inverse multiply A equal to the identity matrix, then it is equal to A times the same inverse. It also equals to the identity matrix. Okay. And then the thing is that not all the matrices have inverses, right? So in order for n by n matrix to have inverse, it must have a full rank, right? Because if you use A minus times A, the identity matrix is full rank, right? That means A is full rank. So if A is not full rank, we have something called pseudo-inverse, which we'll cover a little bit more in detail when we need that. Okay. And then a matrix is called invertible or non-singular if the inverse exists. Otherwise, we call the matrix singular. Okay. Yeah. And there are some properties of inverse. Most of them should be pretty straightforward. The thing is, if you have A times B inverse, then it is equal to B inverse times inverse, right? You need to flip these two matrices, okay? And you can verify that easily. Okay. Then for a linear system, AX equals to B, if A is invertible, then X equals to A inverse times B, right? So this is when you solve linear equations, and then if A is full rank, then you can just take the inverse on both sides, right? So maybe let me ask you guys a follow-up question just to test you real quick, right? So if A is not full rank, does this linear system has a solution or it depends?
It depends.
It can have, when does the AX equals to B has a solution when A is not full rank?
When B is in column space of A.
Yeah, exactly, right? So when B is in the column space of A, then B can be expressed as linear combinations of the columns of A. Yeah. Okay, great. Okay, so then let's quickly talk about determinant, right? So how do you sort of geometrically interpret determinant? You can think about determinant as the signed volume formed by the vectors of matrix A. Okay, so let's say we are in 2D, and then we have two vectors, V1, V2. These two vectors are the columns of the columns of A, right? Okay. So the determinant represent this area formed by V1 and V2. Okay. And also you know that the determinant can be negative, right? But the volume is always positive, right? So when does the determinant becomes negative? Yeah, exactly. When you flip the order of V1 and V2, right? So here V1 is to the right of V2. V1 is to the left of V2. Then the determinant is negative. Okay. And in high dimensional space, the determinant represent the parallel peptide. Okay. Maybe someone can pronounce it better, right? Yeah. So a generalization to high dimension is a parallelepiped. Okay. And then you know that sometimes determinant can be zero, right? So that means the volume is zero, right? So intuitively that means the columns must be linearly independent when the determinant is zero. Right. So when the columns are linearly independent, that means the number of dimension collapse to a lower dimensional subspace. Right. That's why you can think about if in 3D the three vectors are linearly independent, you collapse it to a hyperplane. Right. So that's sort of the intuition behind it. Okay, and then yeah. So this is just a quick overview. When the determinant is zero, the transformation collapse, right, to a lower dimensional space. When the determinant is strictly greater than zero, the orientation of the vector is preserved, right? So in 3D, you can use the right hand rule, right? It is consistent with your right hand, then the direction is preserved. Otherwise, the direction is reversed. Okay. There is another application of determinant when you can use that to calculate matrix inverse. But numerically, no one uses this to calculate matrix inverse. Perhaps other methods like Gaussian elimination is more efficient. But then it serves as a good way of understanding the determinant. Right? So If you want to calculate the matrix inverse, then you could use what is called the adjoint matrix divided by the determinant of A. Okay, and there is even a geometric intuition behind this adjoint way of calculating the inverse. You can check this YouTube channel I recommended. Okay. And again, the calculations are not so important. It's more about the properties. You can always use a Python package to calculate the determinant. Okay, and then it has already been brought up. What is a vector space of matrix M times N? The column space or the range space, sometimes people call it, is the span of the columns of A, right? So when you have A is M times N, where you have M rows and N columns, the column space is all the possible linear combinations of the columns of A, right? So you can denote this as A times X, where X is all the vectors in Rn, right? And the dimension equals to the rank of A, right? Since you are talking about the span of all the columns of matrix A. And if you are talking about row space, that means the linear combination of the row vectors of A. So that simply is A transpose Y, where Y is all the vectors in Rm. Okay. For symmetric matrices, then of course the column space equals to the row space because A equals to A transpose, right? Yeah, and then the null space is all the vectors X such that AX equals to 0, right? Okay. And the dimension equals to n minus the rank of A, right? This is an important property in linear algebra. So this is an orthogonal property. The row space and the null space of A are orthogonal complements in Rn. Okay. Yeah. So if you can, in other words, you can decompose. You can decompose the space by vectors in the row space and vectors in the null space. Okay. Yeah, and then the column space and the left null space are orthogonal elements in Rm. So this should be a typo here, I think. Okay. Yeah. Yeah, then I will talk briefly about eigenvalues and eigenvectors. Right? So usually when we define eigenvalue and eigenvector, it is a square matrix. Right? A is an n by n matrix, and if there exists a scalar and a non-zero vector v such that AV equals to lambda v, right? Then v is called the eigenvector, lambda is called the eigenvalue, right? Again, there is also a geometric intuition to eigenvalue and eigenvector. You can view, if you view matrix A as a linear transformation to vector space, right? So eigenvectors are those vectors that remain in the same direction after the linear transformation, right? So if you transform V by matrix A, they still remain largely on the same line, not exactly on the same line, right? So that is a eigenvector. And how to calculate eigenvectors? You could view this as AV equals to lambda times the identity matrix times V, right? And then you move the A minus lambda I to the left-hand side, right? So if this linear system are going to have solution, then the determinant must be 0, right? Otherwise, V must be a 0 vector. So you can solve this, what is called a characteristic polynomial, to get the eigenvalues, right? And then you can plug the eigenvalue to get the corresponding eigenvectors. Okay, so you could do some simple exercise just to familiarize yourself with it. Okay, any questions so far? Okay. Yeah, and then there are some connections between eigenvalues and the trace of the matrix and the determinant of the matrix. So if you sum over all the eigen values, it is equal to the trace of the matrix. And then if you multiply all the eigenvalues, it is equal to the determinant, right? So remember that the determinant represents the volume of this linear transformation, okay? And then if you multiply all the eigenvalue together, that means all the eigenvalue kind of gives you how much you are stretching each dimension, right? So and then you multiply together, that gives you the overall volume, how much you are stretching this whole, let's say, 3D or ND space. Okay, and one of the property is that eigenvectors corresponding to distinct eigenvalues are linearly independent. You can show this from the property, right? So usually you can show by contradiction, assume they are linearly dependent, and then you can get a contradiction. Okay, and then this slide is just about definition. What does it mean by positive semi-definite? What does it mean by negative semi-definite, right? So we say a symmetric matrix A equals to A transpose. It is called positive semi-definite if pick any vector in Rn, X transpose AX must be greater than or equal to 0, right? Okay. And this property will be used in optimization when we talk about semi-definite programming, where the variables satisfy this positive semi-definite constraint. Okay. And then positive definite means instead of saying it is greater than or equal to 0, then it is strictly greater than 0 for all non-zero vectors x. Right. So that means all the eigenvalues of A are strictly greater than 0, and this positive semi-definite means the eigenvalues are greater than or equal to 0. You can make an analogy on negative semi-definite and negative definite matrix. And then if a matrix is indefinite, if it has both positive and negative eigenvalues. This slide is just about definition. Okay, so this slide is perhaps more interesting. Did you guys study eigenvalue decomposition in the previous semester? Okay, so if you have a symmetric matrix, and then you can decompose this matrix using eigenvalue decomposition, where the Q matrix are what is called orthogonal matrices, right? Orthogonal matrices means QQ transpose equals to the identity matrix, right? Meaning all the columns of Q are orthogonal to each other. Okay, that means if you multiply the same column, that equals to 1. Otherwise, the inner product equal to 0. Right? That means they are orthogonal. And this lambda matrix is a diagonal matrix with all the eigenvalues, right? And then each of these columns of Q correspond to its eigenvectors. Okay, and you could write this product using this outer product form. Right? You can quickly check this is true, where Qi is the qth eigenvector, right? So if you have Qi times Qi transpose, this is like taking outer product of Qi itself, right? So that gives you the decomposition, right? So the way to think about this is for any symmetric matrix A, this is a way of decomposing matrix A into n rank 1 matrices, right? So because Qi itself is a single vector, right? So therefore Qi times Qi transpose is a rank 1 matrix. Right? So this is a way where you could decompose A into n rank 1 matrices. And then there are a few other properties. When A is symmetric, then you can show that all the eigenvalues are real, right? Why this is not trivial? Because when you solve this characteristic polynomial, it is a high-order polynomial. Not necessarily all the roots to that polynomial are real number, right? You could have complex numbers, but then if A is symmetric, you can show that all the eigenvalues are real. And of course, when A is PSD, then all the lambda s are greater than or equal to 0. Right? So this is a property we will be using when we talk about semi-definite programming. Okay, so that's all I want to cover for linear algebra. Probably, linear algebra is, let's say, more useful than calculus in this class. That's why I spend, let's say, 60% of the time on linear algebra. Then I will talk a little bit about calculus. Any comments or questions so far? Okay, yeah. So if you're not so familiar with linear algebra, you could use this as a cheat sheet. But it would be better if you understand the geometric intuition for most of the concepts, and then you can use that in a nice way when you want to solve some optimization problems. Okay, yeah. Okay, so let's talk a bit about a couple of theorems in calculus. When we define a function that is a mapping from a domain A to B, right? So you can maybe treat A and B as two sets, right? Of course, the sets can be Rn itself. So the mapping from Rn to Rm means that F maps some n-dimensional vector to an m-dimensional vector, right? It does not mean that m is defined for f of x is defined for all x in Rn. It could be defined for a subset of Rn, right? Like this logarithmic function, where you only define log of x on the domain of where x is strictly greater than 0. Okay. And then how do you define continuity of functions? Right. So usually the way to define that is using this epsilon and delta notation. Has everyone studied this notation in previous lecture? How many people have studied the epsilon delta notation? Just quick show hands. Okay, yeah, maybe not every one of the people have done that before. So let me just to give a very quick review of this notation here, right? So the way you want to define a continuity function, right? Of course, intuitively you could let's say how do you show a function is continuous or not? Let's say this function is continuous, and then here, maybe let's say at x equals to 2, it is, it has, let's say, a jump here at x equals to 2, right? And then intuitively, you could define, let's say, when a function is continuous at x equals to 2, you could say, for any sequence that converges to x equals to 2, the function value converges to a given value, right? So here, as you can see, when x approaches 2, it converges to a unique value, right? But then for this function, when x goes to equal to 2, you cannot see it converge to a given value, right? Because at this point, it has like a jump here, right? Then for some point, people just use limit to define continuity of functions. But then I think there are some paradox that was discovered when you just use a limit. Then I believe it's Cauchy who invented this epsilon and delta notation, where basically you can think about the epsilon delta notation as a rigorous way of defining things like limit of sequences or continuity of functions, and even if you want to define derivatives in a mathematical rigorous way, you need the epsilon delta notations. Okay, but anyways, you could take a look at this definition, sort of to intuitively understand why this is true. Okay, so it says a function is continuous at a given point x in a domain. So let's say using this example here, we are talking about x equals to 2 here. Then it says, so this notation here, this means for all. And then this notation means there exists. hopefully most people have done this before. Okay, so it says for all or for any epsilon that is strictly greater than 0, there always exists a delta that is strictly greater than 0, such that for all the y, where y and x the distance is less than or equal to delta, right? Then f x and y is less than or equal to epsilon, right? So if you are going to write this epsilon delta notation in English, that means, let's say, for all the y's, let's say y's that are let's say quote close enough x, fy is close to f of x. Okay, that's basically what this epsilon delta notation says. Where you can pick any arbitrary epsilon, right? As long as epsilon is greater than 0, let's say you pick epsilon as small as possible. Then you can always find the delta such that when y is close enough to x, bounded by delta here, then the function value of y will be close enough to x, f of x. Right? That's sort of the intuition here. With that, you can have a rigorous definition of continuity of function. And then similarly, you can use this to define things like a limit. Okay. And you can verify this with this very small example here. Like, for example, here, if you have a discontinuity here, pick any epsilon, you cannot find the delta because no matter how small the delta is, you will still have this jump here, right? So that means this function is discontinuous. Yeah, and then a sort of a less rigorous way to define continuity through limit, where you can have, let's say you have a sequence that converges to the point x. As this sequence goes to infinity, then f of xi will converge to, you can bring the limit inside. That means the function is continuous. Okay. And when we say a function is continuous, then it is continuous at every point in its domain. Right? You can go through all the epsilon delta argument for the whole domain. Okay. Any questions here? Yeah, and similarly, how do you define the derivative of a function? You can also define it through limit, where you have a vector h that goes to 0, and then if fx plus h minus fx minus this differential of fx times h divided by the norm at h go to 0, then you see if the limit exists, and then there is a linear operator applied to function f, then you see the function is differentiable. And then differentiability imply continuity, right? You can also show that using the epsilon delta way of doing things. Okay. So we are not going to the details of those resulting analysis. In this class, we won't be using too much the epsilon delta way of doing things. It's more, you can just assume all the functions we gave you are differentiable, right? Okay. So if a function is differentiable, how do you calculate how do you differentiate its function, right? The easiest way is you just calculate the gradient of a given function, right? So the gradient is defined as a column vector, right? So you have a function that maps Rn to R, then the gradient is take the partial derivative of each of the variables that defines f, right? So you should be pretty familiar with this. Okay.
Shouldn't
Yeah.
your gradient be the nth dimensional?
Huh?
So your gradient of function is a n-dimensional.
Yeah. It's an n-dimensional vector. Yeah.
So it should map from Rn to Rn, not Rn to Rn.
Oh yeah, sorry. Yeah. So the function is Rn to R, and then the gradient is Rn to Rn. Yeah. Yeah. Yeah, you are right. Yeah. Okay. Okay. So what is interpretation of the gradient? So you can interpret the gradient as the direction where the function value will increase the maximum increase of the function. Okay. So how do you show that? Maybe you could show that using what is called the directional derivative. Right? So when you take the directional derivative of a function, that is a dot product between the gradient and the direction you are taking the derivative. Right? So if you take the same direction as the gradient, that gives you the maximum improvement. Okay? And then you also define things like C1 functions, right? For most of the functions we deal with, especially if you are talking about gradient-based methods, we assume those functions are C1 functions. So C1 function means f is differentiable on the domain, and then the derivative is also continuous, right? Not just the function itself is continuous. The gradient exists. The function is differentiable, and the derivative is also continuous. That's typically the functions we deal with. Okay. And then another word you will read from the optimization literature is people call it smooth functions. Right? So if a function is C1, it is called smooth functions. There is a whole area called non-smooth optimization where people try to handle what if the function is non-smooth. How do you come up with algorithms? We will probably only talk about maybe one or two algorithms on non-smooth functions. Most of the algorithms are on smooth functions. Okay. Yeah, so here is one more definition. What is the Hessian of a function? Right? So if a function from Rn to R is twice differentiable, right? Meaning that the second order derivative also exists, right? So for the sake of the argument, let's also assume the second order derivative is also continuous. Then you can write down this Hessian matrix, and each entry of this matrix is taking the partial derivative of xi, then taking the partial derivative of xj, right? So you know that if f is twice continuously differentiable, then this matrix is symmetric, right? Because partial derivatives order doesn't matter. You take derivative with x1, then x2 is equal to x2, x1, right? Same thing. Okay. Yeah, and then as you can see, this is a symmetric matrix. Then we will discuss when it is positive, semi-definite, and so forth. And that is an important property in optimization. We will talk about that maybe in the next two lectures. Yeah, so here's probably what you heard the most in a calculus class, right? So if you only study calculus, perhaps you believe that Taylor is the most important mathematician out there, right? So everything is about Taylor series expansion. So the idea is you could approximate any arbitrary nonlinear functions using polynomial functions, right? So typically we only talk about the second order Taylor series expansion. So here, let's assume you have f, which is a mapping between n dimension to one dimension. And then you want to perturb this vector x a little bit by vector h. And then you can approximate this using a quadratic function where you have this zero order term, just evaluate the function at the point x. Then you take the derivative at this current point x times the perturbation, and then you have 1 over 2 h transpose the Hessian times h, right? So this is like a second order curvature of the function. Okay, and the small h is like the displacement vector, right? The amount you are going to perturb the vector x. Okay. Yeah. So Taylor series expansion would be quite useful in deriving some of the algorithm we are going to use, like Newton's method. Then since if you only expand this to the second order, there will be what is called the remainders to the Taylor series expansion, right? So there are two typical forms people use. One is called the Pinot form in Taylor series. The other called the Lagrangian form. Okay, so have people studied this before previous semester? Oh, okay, yeah. So you can assume this is a rigorous way of approximating the function, right? Because you know Taylor series expansion still has some errors, right? Because it is an approximation, but then how do you have a way to characterize the approximation? To what extent you are approximating that, right? So you could write down this Pinot form and the Lagrangian form in a general way, where first you write down this is nothing but a Taylor series expansion, right? And this R2 is called the remainder form, which gives you the error of the Taylor series, the second order Taylor series expansion, right? The first form of this remainder is called Pinot form, where it is sort of an asymptotic way to approximate the remainder, where you see the remainder grows with respect to h raised to the power of 2 as h goes to 0, right? So that means this order is smaller than h to the power of 2, right? So in other words, as h goes to 0, the remainder will go to 0 faster than h squared, okay? Because you already have a square term here, then the remainder term will goes to 0 faster than h squared, okay? That's sort of intuition of this Pinot form, okay? And then another form that will be used in some of the proof we are going to talk about is the Lagrange form, where you know that if you use the Hessian and the gradient here, it will be an approximation. But the Lagrange form gives you an exact approximation, where you say you are still going to use the gradient, but then for the Hessian, you are not going to use a Hessian at x, but use a Hessian where it is evaluated at somewhere between x and h. Okay, so we are taking the combination of x and x plus h. So using this theta parameter, which is between 0 and 1 here. Okay, so in other words, what you know about is if you use the Hessian evaluate at h, it will not be exact, right? But you know that the exact Hessian is somewhere between x and x plus h, right? That's why you have this theta parameter here between 0 and 1, right? When theta is equal to 0, then you have the Hessian at x, right? When theta equals to 1, you have x, the Hessian at x plus h. But what you know is that there exists a theta between 0 and 1 that will give you the exact approximation. Okay. Yeah. So another theorem in calculus, perhaps you have studied this before, called mean value theorem. Did you cover this in the previous semester? Okay. So you can view mean value theorem as Taylor series with Lagrangian remainder applied to first order Taylor series expansion. Okay, that may confuse you even more, but maybe let me maybe draw a figure to show you the intuition here. Okay, so let's say you have a function f, right? Okay, so now let's consider 2 points in this function x and y. Right? So here the function value is f of x, and this is f of y. Okay. So now on the left-hand side, let's consider the difference between fy and fx, right? Okay. So the difference is essentially this part, right? Yeah. On the left-hand side, on the right-hand side, let's first ignore this term. Just consider x and y, right? So I want to multiply y minus x by a slope such that y minus x times this slope equals to the changes in the function value, right? So you know that this slope should be, let's say, change a different color. This slope should be something like this, right? You connect these 2 points, the slope should be the same direction as this line segment here, because that evaluates the difference of fx and fy, right? So what it says is there exists a gradient, right? So there exists a gradient of f evaluated as somewhere between x and y, right? So this is x, this is theta between 0, 1 times y minus x, right? Again, so when you have theta equals to 0, then this is nothing but the gradient at x, right? When you have theta equals to 1, this term is nothing but the gradient at y, right? So what this theorem says is that there exists a theta between 0, 1 such that if I take the gradient at that point, it will have the same slope as this line segment here, right? Clearly, it's you can find such a gradient, maybe let's say at this particular point, take the gradient here, it is parallel to the line segment between x and y, right? That's what mean value theorem says, right? That means in words, if you take 2 arbitrary values, you can always find the gradient of the function that is between x and y. This gradient is equal to you use x and y divided by y minus x, right? So of course in high dimension you cannot divide the vectors back, but you get the intuition. That means there exists a point where this gradient will give you the exact function value change, right? So you can view this as a special case, or maybe you can view this as a special case of Taylor series expansion with Lagrangian remainders, because here we are talking about an interpolation of Hessians. This is like a second order mean value theorem, all right? And then the mean value theorem holds for any arbitrary order, right? So the mean value theorem is nothing but the Lagrangian form applied to the first order, right? Instead of approximating the Hessian, you approximate the gradient, okay? So this is a very useful theorem to remember when you try to prove some properties, okay? And then we will go to a few more definitions. So if you have a function in high dimension where you map n-dimensional vector to an m-dimensional vector, right? So suppose you have m different functions, f1 all the way to f of m, then the Jacobian matrix of a function is defined as follows, where each row of this Jacobian matrix represent the gradient transpose of the S function, okay? And then you have in total m different functions. Yeah. And then if m equals to n and jf of x is invertible, then you know that f is locally invertible near x, okay? Yeah, so here let's talk a bit about chain rule. You should be pretty familiar with that because I assume most of the engineering math class will teach you how to do the calculations. Let's say if you are talking about chain rule in scalar form, you want to take this composition of function f of x and g of x, and take the derivative with respect to x, you first differentiate f and then you differentiate g, right? And that's a simple chain rule in scalar form. And then if you want to consider chain rule in matrix form, then you will have to use the Jacobian matrix, right? So you could verify this is true here. Yeah, and then what about chain rule for second order derivative? It's in general not so trivial to do, but then we give you two special cases. One is composition with a scalar function, and then the other is composition with affine function. Those are most commonly used in optimization. You could verify that. I'm not going to the detail. This is just a matter of calculation. Okay. So what about references? If you want to know a little bit more, I will recommend the three references. The first one is a classic convex optimization book. In the appendix of the book, they give you reviews of linear algebra and calculus. And then there is a nice linear algebra review by Zico Kota. I took some of the linear algebra notes from this note. Right? Again, I would strongly recommend getting some geometric intuition by watching the YouTube videos. It's not so easy to draw you a picture on 2D, but in those videos, they will show you things on 3D to help you get some intuitions. Okay. Any questions? Okay.